All right, in this problem you have the body temperature model. It's based off of Newton's law of cooling, which is a thermal law. You use it in general chemistry. You should be using it in general chemistry for thermal equilibrium, and they should be talking about it there. If you didn't talk about it there and you have the opportunity to take physical chemistry, you definitely will talk about it there. So just to remind you, we had initially looked at a rule of thumb that people use in forensic science to estimate time of death. We realized that the rule of thumb sucks, and we came up with a better model. I don't think everybody completed that assignment properly. I keep handing it back, but hopefully going through this number 3 now will help you go back to that in-class assignment and finish it up. So this is the better model. The problem is it's a more complex model, so it's harder to work with. The model has what we call 3 parameters. This parameter C, the parameter R, and the parameter K. And they're dependent on the situation at hand. K is room temperature, because as time goes to infinity, you would expect that the body would cool down to room temperature, and that's where you want it to level off at. We call that an asymptote, but in chemistry and biology, we call this a saturation point. So we want it to saturate at the temperature of the room, and that's the concept of thermal equilibrium. If you have a small body inside a larger body, whatever the medium is, and you put the smaller body inside that larger body, the temperature of the smaller body will achieve equilibrium at the temperature of the larger medium. So just for the sake of running this through, we're going to assume that K is 70 degrees. Although in our room in Richardson Hall, I believe that this K has been as high as 90 degrees in the dead of winter and probably 100 degrees in the summer. But we, in general, in most places that we walk around, this K, the room temperature, is 70. So we're going to set K equal to 70. The first step to get rid of the parameters and apply the data in case 7 is to plug T equals 0. That's what we call the baseline condition. The baseline condition was what the body temperature was at time of death. So the numbers in this data set unfortunately come from death row. That's why you have the times set at 9 a.m., 10 a.m., and all the bodies were achieving this at the same time. But it puts the data into context, because I think people were confused where those numbers came from and how to explain those numbers in the table. Now T equals 0, when we plug it in, we get C times 1 plus 70, because e to the 0 is always 1. So that's why we get the 1 here. And then I get C plus 70 because C times 1 is 1. Now, we need to solve for C, so we're going to use the Y value at baseline from the table, which was 98.5 at 9 o'clock. So I got this to the in the table right in that first column, rectal temperature 98.5. Now I can solve for C. C is 28.5. So here's where I'm at right now. I have the value of C. See this C here? It's 28.5. That parameter's resolved. Now I'm only one parameter left. That's R. So I'm going to solve for R by using data from the table at T equals 1. T equals 1 would be 10 a.m. because time of death was 9 a.m. So 1 hour later would be represented by 10 a.m. So I go to the data table at 10 a.m. I plug in 1 into this formula, and I get this 97.2 from the table. And now I'm going to solve for this R by isolating e to the minus r. So the first thing that has to go is the plus 70. So I subtract the plus 70 from both sides, and I get the right side is equal to 27.2, and the left side is 28.5 e to the minus r. Okay, So now I copied this previous formula. We have 28.5 e to the minus r is 27.2. I'm going to divide both sides by this 28.5 to arrive at this expression. And that's around 0.95, not 95. I don't know why the point disappeared here. So I have e to the minus r is around 0.95. The point is here. So now I ln both sides to get at this minus r. And minus r is natural log of 0.95, which is approximately minus 0.05. So r is minus 0.05. And so now I can plug in r equals minus 0.05, and then I have a new model. Next problem, number 4, asks you to graph that new model. What you'll do is actually plot points. So, for example, at t equals 0, if I plug in 0, I get 98.5. Well, I already knew that because that's the way I found the t equals, I got rid of the parameters in the first place. At t equals 1, I plug in t equals 1 into the formula, I crank out and I get 97.2 as I'm supposed to. At t equals 2, I'll plug t equals 2 into this formula, and I just wrote the answers that I got from the calculator. Now, please make sure you try this on the calculator, because in the past, from the previous pre-calculus class, if they got this wrong because they were typing things into the calculator incorrectly. You should get a graph that looks like this. Now, here what you're seeing is I have it scaled from 90 to 100. If I started my scale at 0, then it would look like a crazy looking graph. I would have a ton of hash marks. So I put the graph going from 90 to 100 on the y-axis. So this is not 0, 0. It's for my bird's eye view, so I can look at the graph and interpret the data. And what I'm seeing is a rapid decline, and I can actually see it starting to slow, which it's supposed to. That's what Newton's law of cooling says. Finally, on number 5, you're asked to find at what time the body temperature was 90 degrees. Well, here's my new model. You can do this algebraically, or you can just continue this table here that you have and just continue it down until you reach about 90. It's not that far away, actually. You can see that you're getting closer. So if I want to solve it algebraically, I take that new model and I set it equal to 90, because this model predicts temperature and I want to know when the temperature is 90. I'm solving for this little t, which is time. So that's what I want to get after. So like before, I subtract the 70 from both sides. I get 20 over here. I divide both sides by 28.5, which is about 0.70. I ln both sides. And natural log of 0.70 is about negative 0.35. And I come up with around 7 hours. So I went through this a little bit more quickly because it's the same calculation I did to find r, except in this case I'm finding t. So nothing different here. I'm trying to isolate the exponential term, and then I ln both sides. So it's a pretty routine crank that you're running through. And so that gives us the answer for this problem. And I think this is very clearly explained now. So the in-class assignment I gave you originally on the body temperature, this is what I refer to as the new model. It will now work for any other case. I fit the data to one case, and now I'm going to use it for all the cases as a prediction model. So in this way, I think some people were confused what I meant by new model and what they felt that they had to solve for r every time. You don't. The r you get, obviously, using different data will be slightly different, but it shouldn't be that far away from minus 0.05. So I've seen anything from between minus 0.025 to minus 0.05. That's about the range that these r's come under. All right, now I'm going to save this as a module, and you can look at the next one for the final problem, which was on graphing.